Imagine spending years, engineering the most mathematically complex, rigorous memory system for a neural network. You've derived continuous time formulas, you've optimized
Right,
matrices.
the whole 9 yards of mathematical rigor.
Exactly. You do all of that to guarantee long-range memory, and you achieve state-of-the-art results. But then imagine finding out that simply letting a basic vanilla transformer, like read the data a few times beforehand, completely obliterates your highly engineered results.
Well, it's a pretty harsh reality check for the field.
It really is. Today, we're looking at what might be a massive blind spot in how the machine learning community evaluates architectures. Our mission is to unpack a paradigm-shifting paper from researchers at Tel Aviv University and IBM Research.
Yeah, the paper is titled Never Trained from Scratch. Fair comparison of long sequence models requires data-driven priors.
And because you, our listener, are navigating the bleeding edge of machine learning and data science, you already know that evaluating models is fraught with methodological pitfalls. But, this one might be the biggest we've seen in years.
It genuinely shakes the foundation of how we benchmark long sequence models. For a few years now, the accepted wisdom in the field has just been that vanilla transformers fundamentally fail at modeling long-range dependencies.
Right, which is the perceived failure that paved the way for the rise of state space models, or SSMs, like S4.
Exactly. We've collectively spent thousands of hours engineering workarounds for the transformer's supposed limitations. But the research we're diving into today proves that this performance gap is, well, it's largely an illusion. It's really just an artifact of random initialization.
Okay, let's unpack this. To really understand the magnitude of this blind spot, we need to look at how these models are actually being tested. The gold standard stress test for long-range dependencies is the long-range arena benchmark, right? LRA.
Yeah, LRA is the go-to, but the baseline logic there is flawed.
I'm struggling with the baseline logic myself. Like, if researchers know that foundation models, which are mostly transformers, get their power from massive pre-training, why on earth do they benchmark them on LRA from scratch? It seems designed to make the transformer fail.
Well, the rationale actually comes from a place of scientific rigor, even if the outcome ends up being flawed. When researchers develop a new architecture, say, an SSM designed with specific inductive biases to handle sequences of 10,000 tokens.
Right, they want to measure the raw capability of that specific architecture.
Exactly. So to do that, the community established a standard methodology where you train the model from scratch using random initialization. The goal is to decouple the effects of massive pre-training data to allow an apples-to-apples comparison.
The logic being, if you let a transformer pre-train on half the internet but force a new SSM to start from scratch, you aren't measuring the architecture anymore.
Right, you are just measuring the data set.
But there's a glaring discrepancy when we look at the real world. Foundation models like AlphaFold predicting complex protein structures or autoregressive models doing code completion, they're deployed everywhere.
Yeah, and they display remarkable long-range capabilities.
Exactly. If the raw transformer architecture was inherently incapable of long-range dependency modeling, those tools simply wouldn't work, regardless of how much data you threw at them.
That contradiction is exactly what the Tel Aviv and IBM researchers zeroed in on. The subpar performance of transformers on the LRA benchmark isn't a fundamental flaw in the attention mechanism itself.
So it is strictly a byproduct of the random initialization.
Completely. When you initialize randomly and train only using downstream supervision, you completely disregard the mechanical role of the pre-training objective. Pre-training doesn't just, inject facts or world knowledge into the model.
It structurally shapes the inductive bias.
Precisely. It aligns the internal representation so the model can capture relationships across a sequence.
Wait, if we are building models to capture long-range dependencies, doesn't random initialization essentially force the model to learn the fundamental structure of the data A&D, the downstream task, at the same exact time?
Yes, exactly.
It's like asking an algorithm to solve a complex calculus problem in a language it just started learning today, instead of teaching it the syntax first.
It's actually worse than that. It's not just learning a new language. It's being asked to infer the fundamental laws of physics from scratch while blindfolded, simply by being told whether an answer is right or wrong.
Wow.
You are forcing the optimization landscape to be unnecessarily hostile and complex. The gradients are trying to figure out what a sequence even means, while also trying to minimize the loss on a highly specific classification task.
Which brings us to the paper's proposed antidote, self-pretraining, or SPT. This is where the methodology gets really elegant. How does SPT solve this without violating the community's demand for an apples-to-apples comparison?
The brilliant part of SPT is that it acts as a data-driven initialization method, but it strictly uses the downstream tasks training set. It requires absolutely zero external massive corpora.
No gigabytes of web-scraped text.
None. So it perfectly satisfies the LRA constraint. You are only using the data you are already allowed to use.
How does that actually work mechanically? I know they use standard denoising objectives, but what is physically happening to the model weights during this phase? Like, let's say I'm letting the model walk through a maze. Is denoising like letting the model walk through the maze with the lights on a few times to learn the general layout before we turn off the lights and ask it to find the cheese?
That's a highly effective way to visualize it. During the self-pretraining phase, you take the training data and you just corrupt it. For unidirectional models, they utilized a causal autoregressive objective.
Basically asking the model to predict the next token.
Right. And for bidirectional models, they used a masked sequence modeling objective, similar to BERT. You are forcing the model to reconstruct the corrupted data.
But because there is no external label yet, the model is entirely focused on learning the underlying structure of that specific data set.
Exactly. It turns the lights on in the maze.
I noticed the masking ratios they used were heavily tailored to the data type. Like for visual tasks, such as flattening an image into a massive 1D sequence, they masked out 50% of the inputs. But for language tasks, they only masked 15%. Why the huge difference?
It comes down to information density. In language, every single word or character carries a very high degree of semantic weight. If you drop 50% of the characters in a sentence,
It becomes mathematically impossible to reconstruct.
right, 15% is the sweet spot there. But pixels in an image are highly redundant. If you delete a single black pixel in a picture of the night sky, the surrounding pixels make it very easy to guess what's missing.
Oh, I see. So forcing the model to learn the structure of an image requires a much more aggressive masking ratio, like 50%, to actually make the denoising task challenging enough to yield good internal representations.
Exactly. And the results of doing this trigger what we can only call a transformer renaissance. When they applied this simple SBT phase to vanilla transformers, specifically utilizing rotary positional embeddings, the mean absolute performance across the LRA benchmark improved by more than 30%.
30%? That's huge.
Yeah, the average jumped from an abysmal 53.66% to over 86%. For the very first time, vanilla transformers matched the state-of-the-art performance on LRA without a single architectural modification.
They even surpassed well-tuned S4 models on 3 out of the 6 tasks, right?
They did. And we have to contrast this with the alternative approach of just using a massive off-the-shelf pre-trained model. The researchers ran an experiment with Pythia 70M, which is an autoregressive transformer pre-trained on the pile, which is an 800 gigabyte dataset.
You would intuitively assume the model trained on half the internet would dominate the LRA tasks compared to a model pre-trained only on a few thousand task-specific examples.
But it didn't. Pythia 70M actually lagged behind the vanilla transformer that was self-pre-trained directly on the downstream data.
I found this completely counterintuitive. How does an 800 gigabyte model lose to a model trained on a fraction of that data?
It is entirely due to the tokenization clash. LRA tasks require reading data at the absolute lowest level, character level for text or pixel level for images. Pythia, like most modern LLMs, is trained on byte pair encoding.
Right. Grouping common character sequences into single tokens to save compute.
Exactly. So when you take Pythia and force it to suddenly process individual characters or pixels, the distribution shift is massive. The foundation model's learned representations are fundamentally misaligned with the LRA architecture constraints.
But SBT, by contrast, operates directly on the target modality.
Yes, it organically adapts the model to the exact structure and tokenization of the downstream task.
Okay, so SBT rescues the vanilla transformer, but my immediate thought is, what happens to the overachievers? Does this trick supercharge an already state-of-the-art model like the S4 state space model, or does it prove we never needed S4 in the first place?
It does both, depending how you look at it. SPT absolutely benefits S4, improving its performance in 5 out of the 6 LRA tasks. But we really need to highlight the PathX 256 task here.
That's the incredibly challenging visual tracing task, right? Where an image is flattened into an extreme sequence length of 65,536 tokens.
Yeah. Historically, models trained from scratch either fail completely or barely hover around random chance. The previous best reported performance required transferring a knowledge from a shorter task just to hit 63.1%.
And with self-pretraining.
The S4 model achieves an 87.11% accuracy on PathX 256.
Wait, 87% on a sequence of 65,000 tokens. That is a 20 absolute point improvement. It's
It
staggering.
really is.
But this opens up a critical debate about all the mathematical complexity we're injecting into these architectures. To really grasp this, we need to compare the heavily engineered S4 architecture with a much simpler alternative, the diagonal linear RNN, or DLR.
Let's define the difference. The S4 model is mathematically dense. It follows a linear recurrence, generating a hidden state vector across time steps. But instead of using simple learnable matrices, S4 uses a continuous time-inspired parameterization.
Crucially, it relies on the Hipio initialization, right? High-order polynomial projection operators.
Exactly. It is a theoretically derived matrix initialization explicitly designed to guarantee a slow kernel decay over time.
Let me stop you there to make sure we're grounded. When we say slow kernel decay, we essentially mean ensuring that the model doesn't mathematically forget the first token by the time it reaches the 10,000th token, right? The Hipio matrix enforces a strict mathematical long-range memory.
Correct. It mathematically preserves historical context. Now contrast that with the diagonal linear RNN, or DLR. DLR simplifies the architecture immensely.
It uses a diagonal linear RNN without the continuous time parameterization and without the complex Hipio memory guarantees.
Right. It relies on a much simpler initialization. And naturally, when you train them from scratch, DLR lags behind S4 by about 6 average points on the hardest LRA tasks because it lacks those explicit mathematical priors.
S4 averages around 83% and DLR hovers around 77%.
What's fascinating here is what happens when you introduce self-pretraining to both.
Let me guess, it levels the playing field.
Under SBT, the simpler DLR completely closes the performance gap. DLR jumps to an average of 83.37%. It statistically matches the S4 model's trained from scratch performance and only slightly trails the SBT version of S4.
So the data-driven priors learned through the pre-training denoising objective basically render the mathematically rigorous manual biases of S4 mostly redundant.
They do.
So what does this all mean? Does this imply that the ML community has been spending years engineering complex mathematical initializations, writing entire papers on continuous time parameterization, when a simple self-supervised pass over the training data could have solved the memory problem organically?
The evidence strongly points to that conclusion. And to prove why the data-driven priors are outperforming rigid mathematical priors, the authors looked under the hood. They analyzed the learned convolution kernels of the models post-pre-training,
Contrasting the theoretically derived Hipio kernels with the data-driven SBT kernels.
Exactly. The difference in flexibility is striking. Hipio forces a fixed, slow decay rate. It's rigid. But the SBT learned kernels exhibit variable decay rates. They dynamically adapt to the specific modality of the task and the depth of the neural network layer.
Here's where it gets really interesting. If you look at the PathX kernel visualization from the paper, you see this incredible phenomenon. Remember, PathX takes a 128-bit, 128-pixel image and flattens it into a single one-dimensional string of 16,384 tokens.
Right, the model has no idea it's looking at an image.
But when you visualize the kernel learned via SBT, you see distinct periodic spikes in the magnitude. The vertical grid lines of those learned kernel peaks align perfectly with a shift of exactly 128 tokens.
And we have to pause to appreciate why that number matters.
Think about the geometry of that. If you are traversing a 1D string that used to be a 128 by 128 image, jumping exactly 128 tokens means you are landing on the pixel directly underneath your current position in the original 2D grid.
The model organically reconstructed the underlying 2D geometry of the image purely from the denoising objective.
It learned to look up and down without ever being told what a 2D image is.
That visualization is definitive proof of concept. It proves that data-driven priors are far more flexible and ultimately more effective than data-agnostic mathematical ones.
But a skeptical practitioner might push back, right? Like if you're listening to this and thinking, well, of course pre-training helps, but doesn't this just mean they threw more compute at it?
The authors anticipated that exact critique. They conducted a rigorous compute-tied study on the image and text tasks to eliminate the variable of an extended training budget.
Right. They wanted to see if spending your compute budget on pre-training was actually a better return on investment than just training from scratch for twice as long.
Precisely. Or rather, the data proves it unequivocally. They fixed the total number of training epochs across both phases. They discovered that dedicating just 20% of your total training compute budget to the self-pre-training phase outperformed allocating 100% of the compute budget to from-scratch training.
Wow. Let that sink in.
Yeah.
20% on pre-training beats 100% from
The
scratch.
training curves reveal that the model solves the denoising task relatively quickly. Once those internal representations are aligned, the downstream optimization, the actual fine-tuning for the label, accelerates rapidly and stabilizes. It is a far more efficient use of compute.
They also explored how this scales with data availability, which, if we are being honest, is the real bottleneck for most practical applications. We don't always have millions of beautifully labeled examples.
The data scarcity findings are vital for practitioners. They systematically reduce the fraction of available training data, going all the way down to using just 0.5% of the original LRA datasets.
And what did they find?
They found that the relative gains of SBT over from-scratch training actually peak when training data is incredibly scarce. They observed up to a 30% relative gain on very small data fractions.
Why does it work so much better when data is scarce? Does it just prevent overfitting?
It acts as an incredibly powerful regularizer. When data is scarce, a model trained from scratch will quickly memorize the few supervised labels and fail to generalize.
Right.
But the denoising objective forces the model to understand the manifold of the data distribution before it ever looks at a supervised label. It anchors the model in the structure of the data, severely limiting its ability to overfit the specific classification task.
And it is critical to note that these findings are not strictly isolated to the synthetic, gamified constraints of the long-range arena. They validated this across highly diverse signal types.
Yeah, they tested it on the speech commands dataset, which uses raw speech waveforms of 16,000 tokens. There, SBT drove a 5% absolute improvement for transformers.
And on the sequential SciFar-10 task using all three RGB channels, transformers saw an 11% improvement, practically erasing the performance gap with the S4 model entirely.
The speech commands task revealed another fascinating mechanism. They found that SPT mitigated the performance gap between causal and bidirectional variants of S4.
Usually, bidirectional models have an inherent advantage because they can look into the future of the sequence.
Right, but SPT creates such robust internal representations that it compensates for strict directional constraints. The phenomenon holds up regardless of the modality or the architectural directionality.
So, synthesizing everything we've uncovered today, the baseline performance of vanilla architectures on long-range benchmarks has been grossly systematically underestimated by the research community for years.
Completely underestimated, yes.
By simply inserting an inexpensive, data-driven self-pre-training phase using only the task data itself, we obtain a much more accurate, scientifically rigorous evaluation of a model's true capabilities.
It proves conclusively that simpler models, like vanilla transformers with rotary embeddings and diagonal linear RNNs, can match or even surpass highly sophisticated, manually engineered architectures.
And if we connect this to the bigger picture of your daily workflow as a machine learning practitioner, the implication is absolute.
Definitely. Whenever you are designing architectures for multidimensional inputs, algorithmic reasoning tasks, or complex graph structures, incorporating a pre-training stage is no longer an optional step for accurate benchmarking.
It is an essential methodological requirement.
Training from scratch evaluates an architecture's worst-case initialization. Self-pre-training evaluates its actual capacity to model the data manifold.
It really makes you question the broader trajectory of architectural research. If a simple denoising objective over a few thousand examples can successfully replace mathematically optimal continuous time priors, what other highly engineered, state-of-the-art architectural innovations in our field are actually just band-aids compensating for a lack of proper initialization? That is something to keep in mind the next time you are reading a paper claiming a massive breakthrough in model design. Thanks for joining us on this deep dive.